The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So welcome to this week. We're going to talk about number theory. Actually, before I forget, there are some handouts at the very back. So please raise your hand if you don't have any. Then one of us can actually come over and hand you out this sheet, which contains some facts about divisibility. Thanks a lot. And we will be using these throughout the lecture. So today we're going to talk about number theory. And this is a really different way of thinking, actually, but we will use the same concepts as you have learned before, like induction and invariance, stuff like that, to prove all the theorems. So what is number theory? Well, first of all, it's a very old science, one of the oldest mathematical disciplines, and only recently it actually got to have some more practical applications. So what is number theory? It's actually the study of the integers. And what are the integers? Well, these are the numbers 0, 1, 2, 3, and so on. So number theory got, there's some more over here. Another handout over there. So number theory got used actually in cryptography only about 40 years ago. And at the end of the second lecture, we will be talking about this application into cryptography. There are many applications in cryptography, but we will be talking about one of them to show you how useful this actually is. Now, cryptography is the study and practice of hiding numbers, and you can imagine how important that is. We have like medical data that we need to store outside in the cloud, right? So, gee, do we really want that? We actually want to hide our information. We do not want others who are not allowed to see my private information to see it. So this art of hiding information is extremely important, especially nowadays. And number theory actually will help us with it. So number theory is something, you'll be very surprised, that can be used to save, I have to put this on, to save New York City in Die Hard number 3, I believe. So let me start up again. So let's see where it plays. Maybe not.
Yeah, go ahead and grab it. Oh, you're the cop. Then Simon said you're supposed to be helping with this. I'm helping. But when are you going to start helping? After you get the bomb. Don't open it. What? I gotta open it. And it's gonna be all right. Shit! I told you not to open it!
I trust you see the message. It has a proximity circuit, so please don't run.
Yeah, I got it. We're not gonna run. Now we turn this thing off.
On the fountain there should be 2 jugs. Do you see them? A 5-gallon and a 3-gallon. Fill one of the jugs with exactly 4 gallons of water and place it on the scale, and the timer will stop. You must be precise. 1 ounce or more or less will result in detonation. If you're still alive in 5 minutes, we'll speak.
Wait a second! I don't get it. You get it?
No.
Get the jugs. Obviously, we can't fill the 3-gallon jug with 4 gallons of water, right? Obviously. All right, I know. There we go. We fill the 3-gallon jug exactly to the top, right? Okay, now, we pour that 3 gallons into the 5-gallon jug, giving us exactly 3 gallons in the 5-gallon jug, right?
Right. Then
Okay.
what?
Now, take the 3-gallon jug, fill that a third of the way up.
No, he said be precise. Exactly 4 gallons.
Copping 50 miles is running his ass off, and I'm out here playing kids' game to the park.
Hey! You want to focus on the problem at hand?
All right. You can imagine what we are going to do right here, right? So, you can imagine what's below this table. There's a bomb. You guys have to save 604 too. So we have the fountain here. Each tennis ball is 1 gallon of water. We have a big jug, 5 gallons and 3 gallons. So you all got to help me out here. So who has an idea of what we can do? So, well. All right, let's first do that. Fill up the 3-gallon. Let's pour it in the 5. Maybe someone else can continue over there.
If we do the same again, we'll end up with just 1 gallon in the 3-gallon.
Aha, so let's do that. Because it's true, right? We can only fill it up to 5 gallons, so only at most 2 gallons can add to this. Exactly 2 gallons, and 1 gallon is left. All right, next one. You like to? Take out the 5, all right. And then what? Put the 1 over here.
Then fill the 3-gallon and put it into the 5.
All right. That's great. And then fill it up right here. Fantastic. So we actually have 4 gallons here. And luckily we are safe, right? So you saved, thank God, 604 too. So we can continue. So this is actually pretty amazing, though. How can we get 4 gallons out of a 3-gallon jug and a 5-gallon jug? And that's what we are going to talk about in more generality, actually. And if you would just change it a little bit, right, then things would get more difficult. For example, if you would change the 5-gallon jug into a 6-gallon jug, can we still get 4 gallons? No, why not? Everything has to be multiples of 3. That's exactly right. This is a multiple of 3, 1 times 3. This is 2 times 3. So if I do combinations with those, like pouring one into the other completely, or emptying or filling up, we always will have a multiple of 3 gallons in either one of those or both. So we can never have 4 gallons. So this is something that we would like to analyze a little bit more. And to do that, we're going to first of all start with the definition. Actually, you can put up the screen over here. So let me take that out. Can someone up there pull up the screen? Maybe not, maybe later. All right, so let's go with the definition. We say and denote by M and a bar and A, we mean M divides A. And how do we define this? Well, we say that M divides A if and only if there exists an integer k such that A can be written as a multiple of M, namely k times M. So, if you look at this definition, we, for example, have that 3 divides 6, like what we just discussed. There's something interesting going on. Suppose A is equal to 0. Well, any integer will divide A, will divide 0. Why is that? Because I can take k to be equal to 0. So this is equal to 0 times any integer m. So m divides 0 for all integers. So this is kind of the exception, right? And we are going to use this to set up a theorem and analyze this whole situation over here. Now, in order to do that, we will need to sort of define what we can do with all this. So there are states. We will define a state machine. We will see what kind of possible transitions we can have. And once we have modeled all this very precisely, we can start proving stuff. Now, let me first of all write out what our assumptions are. So suppose we have a gallon jug. So in our case, A equals 3. And we have also a B gallon jug. And in our case, B equals 5, right? And we assume that A is at most B. That is sort of the situation that we are working with. And we would like to prove a theorem. Exactly what we noticed over here, that 3 divides both the 3-gallon jug and the 6-gallon jug. We would like to prove something like this. If M divides A, and also M divides B, well, then M should divide any result that I can get with the pouring and emptying and filling those jugs. So this is the theorem that we would like to prove, and we can only do that if we start to have a proper model for this. So let's go for that. And well, the state machine that we're going to use here looks like this. First of all, the states that we have are the number of gallons that are in these two jugs. So we will denote those by pairs. Pairs x comma y. And x denotes the number of gallons in the A gallon jug. The number of gallons in, let me abbreviate that by the A jug. And y is the number of gallons in the B jug. So these are the states, and the start state is exactly as it is right there. We have nothing in either of the jugs, so that's the pair 0, 0. So now we start to build up some mathematics here, right? So we express the state of this whole situation by a pair of numbers. Now we need to find out what we can do with it. So what are the transitions? The transitions are, as we have seen, right? We can just fill one of the jugs, we can empty those, and the other possibility is that we can pour one jug over into the other one as much as we can. So let's write all of those out. We can do emptying. Well, how does that change a state? If we have x gallons in this jug and y gallons in that one, we can transition this into, for example, emptying the A gallon jug. So we will have 0. Or we can empty the B jug. Well, filling is something similar. But now we are actually pouring in more water from the fountain, essentially, right? All those tennis balls here. And we can fill up, say, the A gallon jug up to 8 gallons and leave the B jug as it is. Or we can fill up the B gallon jug and leave the A gallon jug as it is. So these are these two transitions. And the pouring of one jug into the other is actually a little bit more complex. So let's have a look. So how does pouring work? Well, suppose we start with x and y. So let's have a look here. I don't know, suppose we have 2 balls in here and 2 balls in here. Well, in that case, I can say pour all of this over in here, right? So that's easy. But there's also another possibility, whether when I pour all of this over in here, but hey, I can only put in one ball because this is only a 3-gallon jug. So I'm left with only one gallon in that in this jug. So these are two situations that we need to explain. So let's first do the first example that I just did. I pour everything over into the other jug. So we have 0 gallons left in here, and x plus y gallons left in the other jug. And that can only happen if there is sufficient space, right? So this can only happen if x plus y is at most b, which is the capacity of this b-gallon jug. Now, if that's not the case, then I can pour in just a little bit, like just say one ball, like just one of these can go in here. So that's the other case. So xy will actually go to, well, let's just see how that works. How many gallons are left in this b-gallon jug to fill up? Well, we have b minus y gallons left, right? Space left. So we can take b minus y gallons out of this one to fill up this one. So let's do it. We take b minus y gallons out of the A jug and put it all in here, and that makes it completely filled up. So we have b gallons over here. So this is really equal to x plus y minus b, comma b. And this only is possible if we are essentially in the complementary case. So we have that x plus y is at least b, such that there is enough gallons in the A jug to be poured over to fill up the B jug. So these are the two kinds of cases. And of course, by symmetry, we can do also the pouring from the other jug into the first. So let's write all those out as well. So xy can actually go to x plus y comma 0. I pour everything from here to there. And this only holds if x plus y is at most a. Oh. The other possibility is where, exactly as in this case, we can only pour as a minus x gallons over from y into this particular jug. And then this one is completely filled up, and I have a few gallons left over here. So how does that look? Well, we completely fill this up to its capacity. And what is left is y minus, how much did we have to pour in here? Well, that's a minus x. And we again have a similar formula, but it now looks a little bit different. X plus y minus a. And this is only for the case where x plus y is at least a. Okay, so these are all the cases. So maybe there are some questions about this. Is this clear? That we have these different possibilities? Like when we look at these jugs, we can either empty them, filling them up, or we can pour, say, only one ball over up to the full capacity of this jug, or we can just pour everything over into, say, this jug. So those are the different cases that are now fully described by this state machine. So now we can start to prove this theorem over here. So how do we go ahead? Well, we're going to use what you have learned, like induction and invariance. So let's do it. But before actually we do this, let's take this example that we had and see how we can describe all the transitions that we just did, as far as I remember them. So we have that A equals 3, B equals 5, right? We start with empty jugs. We filled up the 5-gallon jug, right? Then we started pouring the 5-gallon jug as much as we could into the 3-gallon jug. So it's one of those rules. We got 3 and 2. Then we emptied the 3-gallon jug. We got 0 and 2. Then we did, what did we do next? Oh yeah, we poured everything into this one. So we have 2, 0 as the next state. We filled up. Actually, I forgot exactly what we did next, but I think we filled up the 5-gallon jug. And then we simply poured over as much as we could from the 5-gallon jug. And we got 3 and 4. And here we are. We got 4 gallons. So what we just did is fully described by this state machine. So let's now try to prove this theorem. So as I said, we're going to use induction. So you always would like to write this out if you solve your problems. What are we going to assume? Well, we assume actually that m divides a and m divides also b. That's the assumption of the theorem, and now we need to prove that m divides any result that we can achieve in this state machine. So what's the invariant that we are thinking about? Invariant is going to be, it's a predicate, and it says something like, if the state xy, if this is the state after n transitions, then we would like to conclude that m divides both x and m divides y. So this is our invariant, and we like to use this to prove our theorem. So how do we start usually, right? So we always start with the base state. Great. So let's do it. The base case is, well, we start with the all zeros, like the empty jugs. It's pretty, well, and we also have paid a little bit of extra attention to what we mean by division over here. We said that all integers actually divide 0. So in particular m divides 0 and 0. So the very initial state, 0, 0, is indeed complying to this particular invariant. So let's write it out. So we have the initial state 0, 0. We know that m divides 0. And therefore, we know that P0 is true. So that's great. So the inductive step. How do we start the inductive step all the time? And we will assume actually P of n, right? So let's assume that. And now we would like to prove P and then n plus 1. So what do we really want to do? We want to say, well, we know that we reached a certain state x, y, for which n divides x and m divides y. Now we would like to show that if we transition to the next state, we again have that same property, that m divides the number of gallons in both jugs once more. And then we can conclude Pn plus 1. So that's how we always proceed. So let's see whether we can write it out in a bit more formal way. Okay, so how do we go ahead? Suppose that x, y is the state after n transitions. Well, what can we conclude? Well, we have the predicate Pn, the invariant, so we know that n divides x and m divides y. And we concluded that because Pn is true. So after another transition, what happens after another transition? So we can conclude that the jugs are filled by the different types of numbers that we see here in this state machine. So let's write them out. So after another transition, each of the jugs is actually filled, are filled with, well, either if I've emptied it, say 0 jugs, 0 gallons, A, B, X, and Y I see appearing over here. And I also notice that I see X plus Y, and X plus Y minus B, and X plus Y minus A. Those are all the different number of gallons that can be in the jugs. Yes, please.
Sorry, what is in our example problem 3 and 5?
In our example, yeah, that's a good question. So in our example problem of 3 and 5, it turns out that the only number that divides both the 3-gallon jug and the 5-gallon jug is actually 1. So in our example, we would have that m equals 1. So over here, we have that only 1 divides A as well as 1 divides B. So m equals 1 in our case. But for example, in the 3-gallon jug and the 6-gallon jug, right, we have that m equals 3. Like 3 divides 3 and 3 divides 6. So those are the two cases that we sort of look at right now. But we put it into a much more general setting, right? We abstract away from the actual numbers and use A and B as representations. Are there any other questions? Yeah. So after another transition, each of the jugs are filled with, well, either 0 gallons, if we have completely emptied them, or we have filled the first A-gallon jug, or it can be B. We also notice that it can be X, of course, it can be Y, because that's the state that we are in. And we can have X plus Y minus A, which appears over here, and X plus Y minus B. So these are all the different possible number of gallons. The X plus Y, oh yeah, that's also present. Is that true? Yeah, that's right. It's X plus Y, so we also have X plus Y. Actually, it's good to check that again. So we have 0, X, Y, A, B, I got those. X plus Y, and X plus Y minus B, and X plus Y minus B. Yeah. So now we can start using our assumptions. So what are they? We have that in order to prove this, right at the top over here, we assume that m divides A and m divides B. So we know that, first of all, m divides 0, of course, but we know that m divides A, we know that m divides B. We have concluded that m divides X and also m divides Y. So if we now use some facts about divisibility on your handout, which we will not prove now, but I think most of them will be on your problem set actually, we can conclude that also linear combination of A, B, X, and Y will be divisible by m. In particular, m will divide X plus Y, m will divide X plus Y minus A, and also X plus Y minus B. So we will conclude that m actually divides any possible result. So divides any of the above. And now we're done. Why is that? Because we have shown now that after the next transition, after we have reached x, y after n steps, then in our n plus 1th step, all that we can achieve is divisible by m, So that's exactly the invariant. So we conclude that Pn plus 1 is true. And so now we're done. Are there any questions about this proof? So this is like the standard technique that we try to use all the time here in this class. We will use it in all the other areas as well, in graph theory in particular. Especially in number theory, we'll also use it, especially in this class. Okay, so let's apply this theorem. Let's think about this movie that we saw, this Die Hard number 3. Die Hard number 4 came out. And then the cast got stuck in Die Hard number 5. That was a problem because the rumors were that in Die Hard number 5 they had like a 33-gallon jug. That's a lot. And a 55-gallon jug. So Bruce has been training his muscles, because you can imagine those are pretty heavy, so if you want to pour one into the other, my goodness. So, but the question is he training the right muscles? So can we apply this theorem now and show that, I should tell you what is the problem. Well, again, he has to get, say, 4 gallons out of these 2 jugs. So is that possible? It's not. I see someone shaking his head. Do you want to explain why?
A and B are both divisible by 11.
Yeah.
So any other configuration will also have to be divisible by 11.
Yeah.
And 4 is not divisible by 11.
Exactly. So 4 is not divisible by 11, so the whole cast got blown up in Die Hard number 5. And so we have no Die Hard number 6 as well. Okay, so now all of this stuff actually helps us to define a new concept as well. So let's do that. I'll put it up here. We will use the terminology GCD of A and B as being the greatest common divisor of A and B. So, for example, if we are looking at A equals 3 and B equals 5, well, then the GCD of 3 and 5 is actually equal to 1. There's no other larger integer that divides both 3 and 5. And other examples are, for example, if we have the GCD of, say, 52 and 44, well, what's this equal to? Well, this actually is 4 times 13. This is 4 times 11. So 4 divides both this and both this one, but nothing larger can divide both of those. So we have that this is equal to 4. We will have a separate definition that talks about this very special case where 2 numbers, if you look at their greatest common divisor, when that greatest common divisor is equal to 1, we actually define those 2 numbers to be relatively prime to one another. So let's put that out over here. So that's another definition. We say that A and B are relatively prime if their greatest common divisor is actually equal to 1. Now, today we will not really use this definition so much, but it's actually very important, and we'll come back to this next lecture. So, if we now look at this particular theorem over here, can we see a nice corollary of this? Like a result, if you think about this greatest common divisor, well, the greatest common divisor of A and B divides both A and B. So the greatest common divisor of A and B will divide any result that we can generate by playing this game with the jugs. So the corollary here is that the GCD of A and B divides any result. Okay, so that's really cool. So this already tells us quite a bit about this game that we have here. So now what we would like to do is to find out what exactly can be reached. We have a property that we have shown here, but what else can we do here? Now it turns out that we can say much more, and we would like to prove the following theorem to make to analyze this whole thing much better. I don't think I need the state machine anymore, so let's take that off. The theorem that we would like to prove is that any linear combination of the, let's change this into the 3 and 5 again, any linear combination of 3 and 5 I can make with these 3 and a 5 gallon jug. So let's write it out. So any linear combination L, which we write as some integer s times a plus some integer t times b. So any linear combination of A and B with, well, of course the number of gallons should fit the largest jug. So with 0 is at most L, is at most B, can be reached. So this theorem we would like to prove now, and in order to do that we would like to already think about some kind of a property that we have. So when we talk about linear combinations, the s and the t can be negative or positive, we really don't care. So for example, we could have like, I don't know, minus 2 times, so for example 4 is equal to minus 2 times 3 plus, actually, is that true? Yeah, plus 2 times 5. So here we have s to be equal to minus 2, and t is equal to 2. And of course a is equal to 3, right? And b equals to 5, is equal to 5. So 4 is a linear combination of these two, and according to the theorem, we can create that number of gallons in this jug. And we already saw that because we did it. But for our theorem, in order to prove this, we really would like s to be positive. So how can we do that? Does anybody have an idea what we could do? Oh,
Does this assume that B is greater than A?
yeah, we have still that A is supposed to be. We will assume that throughout the whole lecture. Thanks. So in order to prove this, we really would like to have s to be positive. So let's just play around a little bit with linear combinations to get a little bit of a feeling for that. How could we write 4 differently as a linear combination of 3 and 5, such that we have actually a positive number over here? Does anybody see another way to see that? Yeah, that's true. 3 times 3 minus 5. So, and how did we do that? Well, we can just add, say, 5 times 3 to this one, and then subtract the same again, minus 3 times 5 over here. And if we add those things together, we will see 5 minus 2 is 3 times 3, as you said, and we have minus 3 plus 2 is actually minus 1 times 5, and this will be a different linear combination of 4. So what we can do here, we can sort of play around and make this S over here, which we now say call S prime, is positive. Actually, it's larger than 0. So let's start a proof for this theorem. It's pretty amazing to me, actually, that you can do so much with a game like this and see so much happening. So let's figure out how this works. Okay. So let's first formalize this particular trick over here. And how do we go ahead with it? Well, notice that we can rewrite L, which is equal to S times A plus T times B, as, you know, we can just add a multiple of B over here, M times B, say, times A, and we can subtract that same amount over here, minus M times A times B. So, do you see what I did over here? I have added M times B times A and subtracted M times A times B. And we did something similar over here, not exactly the same, right? But that's what we did. And you can imagine that we can choose M such that S plus M times B will be larger than 0. We can do that. So essentially this proves to us that there exists an S prime and also a T prime such that L can be rewritten as a linear combination S prime times A plus T prime times B, but now with the extra property that S prime is actually positive. Now this is really important because we're going to create an algorithm of playing with those jugs that can achieve this particular linear combination. And that's how we're going to prove this theorem. So let's assume that 0 is less than L, is less than B. I know that we, in the theorem, we also consider the cases L equals 0 and L equals B, but those are obvious, right? I can either empty the jugs or just fill up the bigger one. So we will consider just this case. All right, so what's the algorithm going to do for us? The algorithm is going to repeatedly fill and pour out jugs in a very special way. And miraculously, we will be able to get the desired linear combination every single time. And of course, we're going to use induction again to prove this property. Okay, so how does the algorithm work? Well, to obtain L gallons, we are going to repeat S prime times, which is the number that we have over here, the following algorithm. First of all, we will fill the A jug. That's one. After we